So continuing with a talk on types of chemical reactions, this I guess is part 2. We've looked at composition, decomposition, and single replacement reactions. The fourth type of reaction would be a double replacement or a double displacement, whichever term you want to use. And I sometimes use abbreviations. So I would put a DR or a DD there for double displacement. I would use a C for composition, D for decomposition, SR for single replacement, and DR for a double replacement reaction. We've looked at some of these in class, hopefully, and they're in the format of what I'm going to call a twosie plus a twosie reacts to form two different twosies. And by twosie I mean, hey, it's made up of a positive and a negative component. So you look at this and you have AX plus BY. And what's going to happen here is you're simply going to exchange the positive portions to form a Y and BX. Remember that the positive part of the molecule is always listed first, the negative last. And the order of the two products does not matter. So the example that we might have used in class would be NaCl plus AgNO3. Sodium chloride and silver nitrate form sodium nitrate and silver chloride. I've told you that you've got to show me two symbols with any of these reactions, with a double displacement reaction. I'm looking for two symbols. I've shown you one, that the reactants are going to yield products. The question is this reaction reversible? Would I put another arrow here pointing in the opposite direction towards the reactants, showing that the reaction is reversible? Or will I indicate something about the products? What I'm looking for? I'm going to look for a precipitate, a gas, or a slightly ionizable product, which right now the only slightly ionizable product that we know is water. Well, water is not one of the products. Do I see a gas? I don't think so. And so you have to know your solubility rules. First family, always soluble. Nitrates, always soluble. Either rule, first family or nitrates, always soluble. But this is the problem. This compound is not soluble. The chlorides are not soluble with silver, mercury, and lead. So we're going to have a precipitate formed here. And the two symbols that I'd be looking for would be the arrow pointing towards the products and then the indication that one of those products, in this case the silver chloride, is a solid. It does not dissolve in water. We'll do more with this later. All right, the last type of reaction then would be called a combustion reaction. And in a combustion reaction, I mentioned this previously. For burning, for a combustion to occur, something must be present. Well, that something is oxygen. At this point, you don't have a lot of information you could use to make combustion reactions, except for this. If you have any type of a hydrocarbon, any compound that contains carbon and hydrogen, like CH4, methane, burning any hydrocarbon, okay, so I'm going to write it in slightly different terms. This hydrocarbon will combine with oxygen and it will always produce carbon dioxide and water. As long as you have a sufficient amount of oxygen present, your products are always going to be carbon dioxide and water. So, if you're looking at this type of reaction, these are all good formulas. Now all you have to do is balance. And to balance them, 1 carbon, 1 carbon. 4 hydrogens, 4 hydrogens. You want to leave your oxygens until the last thing, okay? 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens. And the last thing you balance is the oxygen. And you probably are going to balance it first by looking at how many oxygens you have on your product side. 2 and 2. There's a total of 4 oxygens here. So to get 4 oxygens on this side, I need a 2. So that balances my equation. The combustion reaction, I would probably not abbreviate too much. I would leave it with COMB for combustion. But anytime you have a hydrocarbon, it will produce carbon dioxide and water. And this is real important because a lot of our fuels are hydrocarbons. Methane, ethane, propane tanks, butane, cigarette lighters, and the natural gas that you have coming into your home to provide heat. These are all hydrocarbons. Okay, well and good, I guess. So I've shown you 5 different types of chemical reactions, but what we need for this particular unit is to go back and look at those reactions again. All right? Yes, they are all different types of reactions, but most of them have something in common. Of these 5 reactions, composition, decomposition, single and double displacements, and combustion, 4 of these are always redox reactions. So let me go back and let's look and let's answer the question. Which reactions, let me see if you can see this, okay, which reactions are redox? 4 out of the 5. Let's find them. First, we'll define what does it mean if you have a redox reaction. Well, 2 processes are taking place if it's a redox reaction. I'm going to scoot this up. All right. And the first one of the reactions that takes place is called a reduction. And the other reaction that's taking place is called an oxidation. And for these reactions to occur, they both have to occur simultaneously. You cannot have one without the other. So that's where you get reduction and oxidation forming a redox reaction. Okay? Now, how are you supposed to remember what's going on in a redox reaction? Well, story is long, so I'll skip it for college students and simply say that in an oxidation, you are losing electrons. Losing electrons. Oxidation. And in a reduction, the substance or the chemical is gaining electrons. Gaining electrons is reduction. And how would you remember these 2? Well, you would go to the zoo and you would see your very favorite animals, and the very favorite animal that you have would be Leo the lion. And Leo says grr. Uh-oh, I can't spell grr. G-E-R. Losing electrons, oxidation. gaining electrons reduction. It's just a little mnemonic to help you remember which is which. Leo, grrr. Losing electrons, oxidation. Gaining electrons, reduction. So, how do you know if a reaction is a redox reaction? Let's look at the first example. Yes, it is a composition or a synthesis reaction. That's one way of looking at it. But now ask the question, is it a redox? Well, we know by the oxidation rules. You should have the oxidation rules in your notes. You should go back and read over them. But if you look at the oxidation rules, the oxidation number of a free element is 0. Let me zoom in on this just a little bit. Okay. The oxidation number of a free element is 0. So since sodium is free by itself, it has an oxidation number of 0. Chlorine's also by itself, so it's a free element. But this is a compound, and in a compound, the sum of the oxidation numbers must equal 0. So the sodium is +1, and the chloride component is -1, so that the sum will equal 0. Have these elements changed? Yes. Sodium changed from 0 to +1. How did it do that? Sodium lost an electron. Leo. Sodium underwent the process of oxidation. Leo. By losing an electron, it became more positive. But for the oxidation to occur, there must also be a reduction. And so, if we look for the reduction, it has to be the other component, which is the chlorine. The chlorine went from 0 to -1 because the chlorine gained an electron and underwent reduction. That's what made it more negative. And so both an oxidation and a reduction occurs in this reaction. This reaction is a composition or a synthesis, but it's also a redox reaction. We could do the same thing here. Hydrogen goes from 0 to +1. The phone's just going to ring. Sorry. In this formula. So hydrogen is undergoing oxidation. Losing electrons is oxidation, and the chemical becomes more positive. Meanwhile, oxygen goes from 0 to -2. That's how the oxidation numbers sum in this compound to equal 0, because 2 plus 1s and a -2 sum to equal 0. And so the oxygen is undergoing the process of reduction because it gains electrons. What's the general trend? Metals like to lose electrons. Metals lose electrons and undergo oxidation. Nonmetals generally gain electrons and are reduced. Let's see then that this is not just a composition reaction, but it's also redox. We'll try one more. Let's go down and look at a single replacement reaction. Let me get this focused here. And for our single replacement reactions, we'll look at this one where the iron is 0 because it's a single free element. But in the compound, the copper is going to be, well, let's see, the chloride is -1 and there's 2 of them, so the copper is going to be +2. All right, so it does look like things change because the copper becomes 0